In this video, I'm going to cover calibration and traceability. If you've watched the other videos about gauges, you'll know that I've shown you how to calibrate or check calibration on pretty much every gauge we've covered, like micrometers, height gauges, indicators, calipers, many more gauges, and the standards that we use to check calibration. In this video, we're actually going to take a higher level look at calibration systems, not so focused on each individual gauge and how you physically calibrate, but how these systems work, why they're designed this way, and how traceability plays into calibration. So we'll be talking about all the gauges and how you should be approaching your calibration system at the company that you work at. Let's get started. We're going to start off with a few definitions just so that we're on the same page. So a calibration compares an instrument to another higher standard. So an example of that would be the instrument would be the micrometer. The higher standard is the Joe block. And that higher standard, the accuracy is already known. It's calibrated. You know what it is. Any variation that you detect between your gauge and your standard must be adjusted until they read the same. So if I'm reading 1 inch and 2/10,000ths with my micrometer, but I know this Joe block is 1 inch, I need to adjust my micrometer until they match. So calibration always involves comparing an instrument against another standard. You're always comparing something to something else. Sometimes it's physical, sometimes it's optical, sometimes it's electronic, depending on what gauges you're working with. But that calibration standard always has a known and accepted accuracy, which is much tighter than your gauge in many cases. So that you're not in question about this. Whatever this says, you trust it because it's calibrated. The accuracy is how close a test measurement value is to the true known value. So calibration maintains accuracy, but it does not typically improve precision. So if you watch the video about precision, gauge R&R, and accuracy, you'll know I spent a lot of time on this. But when you're calibrating, you're not necessarily improving the physical precision. Sometimes repairs during calibration will do that, but typically you're not improving the precision. You're just maintaining the accuracy of what your gauge is measuring. So traceability, it has 4 main components. So first of all, when you're tracking a gauge like this micrometer here, and you want to trace it to the standards that were used to calibrate it, the 4 main components start off with your gauge ID, which is going to be a serial number that you might apply yourself to the gauge, who made it, what model it is, what size, who owns it, what location do they keep it in. These are all identifying parameters. The next step in traceability definition is you're going to need a procedure. You're going to need a written document that defines what you are doing, how you are doing it, under what conditions you are doing it, so that you can apply that procedure to every calibration you do. It's not good enough to say, yeah, it's industry standard. You check a micrometer against a gauge block or a micrometer standard, or you close the micrometer and you check for 0. You need to write that down. You just need to specify. It doesn't have to be incredibly involved in many cases, but it just needs to be written down so that you can reference it. The next step is you need your action and your results. So record any actions you take, including the findings of the gauge. So if you check the gauge and you find it's out of calibration, write down what you measured. Write down what you did to fix it. Did you adjust the sleeve? Did you take it apart and clean it? You don't have to go into large descriptions. Just 1 or 2 words. Yeah, clean gauge, adjusted sleeve, whatever. Note any poor conditions that you may have found it in. If it's rusty, if it's dirty, if it's oily, if there's a chip, If it's damaged, note any of that in your record. And then your verification of the standard. So identify a standard that you used and identify their calibration procedure and their standard. So if you're using the Joe block to verify the micrometer, you need to state, well, everything you know about the Joe block. Is it in calibration? What procedure is used to calibrate it? What equipment is used to calibrate it? When was the last time it was calibrated and when is it due? You need all of that to maintain traceability. Every aspect of the calibration needs to be traced to the higher reference gauge and procedures. So I need to go from the micrometer to the Joe block, from the Joe block to maybe the optical method that it used, the optical method to the standard that the optical method is compared against. So that's how we maintain the traceability. So your basic requirements. First of all, identify gauges for calibration and standards used with a unique serial number on the gauge or the case. So to start off your calibration system, assign a serial number to every tool that is used for final acceptance of measuring parts. If you want to make some things reference only, like a scale, even a tape measure, we'll talk about that in a little bit. You can do that, but anything you know is going to wear and need adjustment over time needs to be calibrated. Even things that are stationary, surface plates, 1, 2, 3 blocks, they move a lot, but we don't think of them as wearing, but they can. Angle blocks. So those all need to be in a calibration schedule. They'll need to have a serial number to identify them. The next step for your calibration system, you need to maintain records of the calibration date, the interval in between calibrations, for example, 3 months or 1 year, 6 months, whatever you decide, and what your result of calibration. Did you adjust it? Did you change? Did you repair it? And what standards and equipment did you use? Number 3, you calibrate following the accepted standards that you have identified. These accepted standards should match what is acceptable to the industry. So you could write your own standard to calibrate something, but if it doesn't match closely to what industry has decided is acceptable, when you get audited, somebody might say, why are you doing it that way when the rest of the industry is doing it this way? Unless yours is advanced, is much more advanced and more accurate, which is unlikely. It's more likely you've chosen a method that is not accurate and is not acceptable. So go ahead and figure out what the industry is doing. Typically the manufacturer of your gauge will state how they do it, what standards they're using, what methods, so you can just follow that, because whatever the manufacturer is doing is going to be, you can probably replicate in one way or another. Then you need to ensure traceability of all calibrations to known standards. So that means documenting what you're using, what standards you're using, what gauges you're calibrating with. Perform all calibrations to the known standards. So do your physical calibration. Clean the gauge, register the anvils. Clean the gauge and the anvils of foreign matter. So as I mentioned in the micrometer video, you can wipe off the anvils with your finger. You can clamp onto a piece of paper and slide it out. For other tools, there's other methods. And then finally, you can perform your calibration or test. Number 8 here, label the gauge calibration status with the gauge ID, the last calibration date, the next calibration date, and who did it. Those 4 items tend to be the ones that are required at a minimum. I think you're allowed to not have who did it, but you definitely need when it was last done and when it was next due. Otherwise you can't pick up, you need to be able to pick up a gauge and look at it to know if it's in calibration or not, at least according to the system. So you need either the next due date and the previous date, the interval, and who did it helps you track down people sometimes if there's questions. So those 4 things on a small label, on the gauge or on the case is fine. Anything you're not going to be, putting in a routine calibration system, put a reference only sticker on it, or a calibration before use sticker. There are some gauges, like gauge pins. I don't have my gauge pins out here handy, but a lot of companies will say calibrate the gauge pins with a micrometer to verify that it hasn't worn before you use it. And so that's a sticker you can apply. A reference only sticker could be for something that's, you're not using for final acceptance. You're just using it for in-process checks, or, when you're investigating an issue, you want to know what the problem is. You're allowed to use some of these reference gauges. And then when you go to put it back in stock after any rework or after any MRB, whatever, you use another gauge that is calibrated. Number 9 is an important one. So suspend gauges from use if calibration warrants it. So if your gauge is failing calibration, you can't repair it at that moment, tag it out, set it aside. Red tags are more than acceptable. There's some other methods, just failing the calibration and leaving the paperwork with it. But make sure that it doesn't get back into rotation and back into use. And number 10, if you do fail, obtain corrective actions on the gauges that fail. So not only correct the gauge, but you may need to re-inspect the material that was used with the failed gauge. So I'll give you an example. This was last calibrated, let's say February 20th, 2019. And so now it's January 30th and 2020, and I'm getting ready to redo my calibration. And so I've been using a gauge, and February 20th rolls around. Okay, it's time to calibrate, and it fails calibration. So sometime between the last official calibration and the current calibration, the gauge failed. So how many parts were measured when the fail condition? When did it fail? We don't know, because normally, what I've always recommended in every video I watch is calibrate a gauge before you use it, or check calibration is a better way to put it. Check that the calibration is in good condition before you use it. Maybe this is a gauge that hasn't been used for a long time. It went out of calibration due to temperature changes. Maybe it was moved. Maybe somebody used it and you didn't realize it and left it dirty, knocked it out of calibration, knocked it out of adjustment, whatever. But now you're in a situation where parts have been measured maybe on January 30th when you used it, and do you need to re-inspect those parts? Do you need to recall them? This is when you start getting an MRB together to discuss what you're going to do. This is why maintaining calibration is good. Maintaining traceability is good, so you can trace what parts were used on the gauge. And as another example, it could be that this micrometer is fine, but this Joe block fails calibration, and I was using this Joe block to calibrate a bunch of other gauges. So if this failed, now I got to trace it to all the gauges that it calibrated. So that's what traceability is for, and it's very important to maintain. So we're going to shift gears a little, and we'll talk about the calibration system standards that are available. So ISO 10012 is the measurement management systems, requirements for measurement processes and measuring equipment. So this is one standard that you should probably take a look at and apply at your company. Most gauge calibration companies are going to follow this standard nowadays. There's some other ones like ANSI, ASQ, M1, American National Standard for Calibration Systems. Those two are not exactly overlapping, but have the same general system. ISO IEC 17025, general requirements for competence of testing and calibration laboratories. So every lab that you send your part to will probably be following this standard, because as time has gone on from in 2020 compared to decades earlier, the ISO standards have become more and more common, as international manufacturing has really grown. Gauges are manufactured all over the world. Manufacturing processes are all over the world. Assembly processes are not necessarily in the same place where manufacturing happens. So the ISO standards have just become a very easy way to coordinate amongst all these manufacturers and gauge companies. And so those two, the ISO 10012 and 17025, are going to be very common. There's also ANSI NCSL Z540.3, the requirements for the calibration of measuring and test equipment. So some other American national standards could still be in use. I expect that some calibration laboratories are still certified to those as well. Depending on your customers and depending on what you want, you may want one standard over another because they are not exactly the same. So I would say we're going to focus on the two ISO standards just overall in this video, but keep in mind there's a few standards out there you should read up on, understand how your gauges are being calibrated, and what you need to do when you're calibrating in-house. You should probably be following the same guidelines. Otherwise, you've got to write your own. So it's easier for you to follow what somebody else did than create your own in many cases. So we talked about traceability a lot already, and this is kind of a visual guide for maintaining traceability. It's called a Traceability Pyramid. And the way I look at it is I work my way from the bottom up. Level 0 is your gauge, what you are using to measure your parts. Could be a micrometer, caliper, indicator, thread gauge, whatever gauge is actually measuring physical parts. And then every gauge you're using should have a gauge standard, that level 1. So a Joe block, a micrometer standard, thread gauges will have set plugs or pitch micrometers, whatever you are using. Setting rings, I don't have any setting rings out, but setting rings for whole micrometers. Whatever you are using in your shop to check the condition of your gauge is a gauge standard. And then your secondary standard will be, we're using the Joe block example, what calibrated the Joe block. So you're probably sending this out to a lab with some sort of optical method to verify the Joe block. So that's level 2. Level 3, well, what verified the optical method? They're going to have a version of a Joe block most likely, maybe some other optical method to make sure that their calibration machine is within its calibration. And then finally you work your way up to the national standard. Whatever the highest level, basically you can work there can be more and more levels in between as you keep verifying standards, but they're all going to be traced back to a national standard. So think about, you've probably heard of, there's a 1 kilogram mass in a vacuum sealed chamber in a mountain. There's a 1 meter bar in a vacuum sealed chamber away from sunlight so that none of this degrades due to exposure to UV light or corrosion. And so those national standards are treated very delicately and used to calibrate some very advanced pieces of equipment. So here's a few examples, and as I said, you could have multiple levels. I show 5 levels on the pyramid. You could have more, you could have less. Some gauges are more directly linked to the national standard than others. So as a level 0 gauge, for example, I said an OD mic. Well, your level 1 gauge will be your cal rod. Next is your optical method. Then your level 3 is your optical standard. And level 4, your 1 meter bar, your national standard. For a height gauge on the right, we could do it with a Joe block. And again, from a Joe block, you go to an optical method, to an optical standard, back to a 1 meter bar. So all of these are being traced back to the 1 meter bar because we're mostly dealing with distance. Other standards might be traced to the kilogram. You're measuring mass. But from this video series, where pretty much everything we're measuring is a distance or a location. So everything's pretty much going to be traceable back to that 1 meter bar. And here's a picture of that. So 1 meter bar, 1 kilogram mass, 1 liter volume. The national standards very closely copy the international standards. So it might be in Switzerland. There's international standards that all of the national standards are made against. And these national standards, each nation should have one. Probably not every nation on the planet, but anyone that's heavily into manufacturing, United States, Europe, Asia, South America. There's manufacturing hubs all over the world, and they should have their own national standard so that they don't have to constantly use, the international standards locked away. They're not going to let anybody really use those, but the national standards are used occasionally for setting up the highest level of equipment. And actually, in recent years, I'd say in the last 10, maybe 20 years, the physical standards are not being used as much as light-based standards. So equipment has gotten so good at measuring the wavelength of light and how far it travels that you can actually use a laser or a certain color of light to calibrate some of this equipment instead of a 1 meter bar. So I think that's pretty interesting. As I mentioned, these standards are typically locked away to prevent them from corroding or degrading, but when you work with metal, what you'll realize, every material you work with relaxes over time. And this 1 meter bar is no different from that. It's going to grow no matter what you do. The molecules, the atoms, they just expand a tiny bit over time, and that's not going to happen with an optical method. So there'll be no material deterioration with those light-based standards. So that's why the industry is moving towards that, and you can have more of them available as well when it's a light-based. So next up, we're gonna talk about how do you choose a standard. In most cases, when you buy the gauge, it almost always comes with a checking standard, so you don't need to really think about it. But sometimes you will when you purchase gauges separate from their standards. So there's a 10-to-1 calibration rule of thumb, which says the instrument used for calibration should be certified 10 times more accurate than the gauge being calibrated. This way, only about 10% of the calibration tolerance is lost to uncertainty, and this is not possible in many cases. So what this is saying is basically, I have a micrometer that's accurate to 1/10,000th of an inch. I need a gauge block that is 10 times more accurate than that to satisfy the 10-to-1 rule. If it's not 10 times more accurate, if it's only 3 or 4 times more accurate, sometimes you got to live with that. As I'll explain, as you get higher and higher levels of accuracy, you can't always maintain 10-to-1. When on that second bullet point, we talk about uncertainty. That deals with every measurement you take, even the calibration measurements. You get a plus or minus, like, okay, this is what I measured, plus or minus a small window. And so when you have a 10 times more accurate, you get a 10 times smaller window. So you lose a little bit. But if you imagine that if this is accurate to 1/10,000th of an inch, and this is accurate to 1/10,000th of an inch, can you really calibrate when they both have the same plus or minus? That's why you want your standards to be at a higher accuracy level, and 10-to-1 is the rule of thumb that has been chosen. I do have another video where I talk about the 10-to-1 rule and the gauge accuracy and R&R, where I go into a lot more detail about the 10-to-1 rule, so please check that one out if you want to learn more about the 10-to-1 rule. It has applications in calibration like this topic. It also has calibrations it also has applications in measurement. So ANSI Z540.2 in 1997, it states that the measurement standard accuracy should maintain the 4:1 ratio or better compared to the calibration tolerance zone. So this is a official standard. The 10:1 rule is just a rule of thumb. You won't find it written anywhere. You can go back to the old military standards. I think it's 120, if I remember correctly. In the 1950s, it stated something close to the 10:1 rule, and it has just proliferated from there. But it's not stated anywhere in writing. It's just become common sense, obviously, and it's a good goal. So, but Z540.2 is the only one that really puts it in writing currently. So the Z540.2 drops 10:1 to 4:1. So now you're losing 25% of your tolerance zone to the uncertainty of the standard. And that is mostly, in 1997, that's a realization that manufacturing has gotten more and more and more precise, and we're reaching the limits of our calibration being 10 times better. Sometimes you can't get 10 times better. You can only get 4 times better, sometimes only 3 times or 1 time better. So, or actually not 1 time better, but the same. So it's a realization that you can't maintain the 10:1 rule as you work your way up that chain of that pyramid of calibration. Next up, when you're talking about your calibration interval, you're going to choose your interval based on purpose of the gauge and degree of use. So obviously the manufacturers have a recommendation. They might say every year, every month, every 3 months, every 3 years. The manufacturer will usually give you that recommendation, but they're not your business. So you may want to choose your own calibration interval. You may want to extend it because you're really not using it that often, and calibration is expensive, and the gauge is very stable. There's no, you don't think it's going to change over time if you extend it. You might want to decrease the interval because you use it a lot, and if that gauge goes out, it's a big problem for you. So you want to check it more often, make sure the parts you're making are correct. So you get to decide it and put it in your calibration system. But you need to justify it. So if you're going to say, yeah, I'm not going to calibrate this surface plate, every year, I'm going to do it every 5 years. You need some justification for that. And you can say, well, it's very, very rarely used. It's in a controlled environment, and the cost of calibration does not justify calibrating every year when we don't use it that much. And our parts, yeah, we need a surface plate for our parts, but our tolerance of our parts is not like super very tight accuracy. So that could be one situation where you might extend it. And then, I might shrink a micrometer because I'm using a micrometer all the time and I want to be certain in it at all times. But when in doubt, if you go with the industry standards because you don't know what to do, that's more than acceptable. Check with your manufacturer. So I have a few recommended intervals that the industry has used, and some of these a little tighter. Calipers, you generally don't see every 3 months. You typically see every year. And because I use calipers so much, I don't want to wait a year to find out, oh, my caliper's out of calibration. I mean, these anvils wear. You use these anvils a lot over and over and over and over again. That the inside jaws will wear, outside jaws, you can damage your depth bar. So I like to check every 3 months. For a caliper, electronic, actually, that's debatable. I would, my internal check I might do every 3 months, and I might send it out once a year for outside vendor calibration. As I said, I want to be in-house. I have the ability to check it on a ring gauge, on a Joe block, And I want to do that every 3 months. But sending it out to calibration to the lab, I'll probably just do once a year to verify that, to get that feedback from the calibration vendor. CMM once a year, ring gauges, gauge blocks, hardness testers, height gauges, indicators. 1 year is fine for those. OD micrometers, bore micrometers. Again, with micrometers, there's a lot of moving parts. Well, not a lot of moving parts, but there's some sensitive moving parts in there. And I frequently need to adjust them because of the conditions that I'm working in are not temperature controlled, humidity controlled, and we're using them a lot on a wide variety of parts. So, excuse me for 1 second. All right. Need to take a little water break. Okay. Next up, micrometer standards. So, not a Joe block, but micrometers above 1 inch will come with a standard. Send those out every year to an outside vendor. Pin gauges once a year or each use, as I mentioned. So you could grab a pin gauge and check it with a micrometer before you use it. And if it's still within manufacturer spec, go ahead and use the pin gauge. Use a calibrated micrometer though. You have to be able to trace it. Surface plate once a year, you could extend that, as I mentioned. Surface roughness comparators or surface roughness electronic measurements 1 year. Roughness standard. Thread plug gauge, thread ring gauge once a year should be okay. If you use ring gauges a lot, they will wear more than plug gauges, so you may want to either have multiple rings available or decrease your calibration ratio, because ring gauges get a lot of wear, and when they wear, there's no adjustment. Well, there's some adjustment, I should say, but when they wear too much, after that, they're pretty much junk. You can refurbish them, but can't reuse them as is without changing. So for methods, you either got outside methods, outside vendors, or different methods you can do in-house. Let me flip back to the first page. Most of these are, gauge blocks, outside vendor gauge blocks. Mic standard is like a gauge block. Cylindrical ring gauge for bore mics. And sometimes you can check, pin gauges and thread wires. You can check with a mic before you use them. Thread plug gauge, you can check with a pitch mic, or thread wires and an OD micrometer. Thread ring gauges, you can do an outside vendor or a set plug. And for thread ring gauges, I typically do an outside vendor because they really have most of the plugs anyway. And they have the expertise to really get that right, that tightness feel. So I like to send those out too. So, why? Why these methods? Why internal? Why external? Why interval, 3 months and a year? It comes down to cost. As I mentioned, there's cost associated with each calibration, whether it's time or actually paying a vendor to do it. Or you have to purchase the calibration equipment. And then you have the acceptable accuracy of the method. So sometimes you can't maintain 10-to-1 or 4-to-1 in-house, and you have to send it out because otherwise you just don't have the equipment. You're not going to invest in it for certain things. Most companies don't have a fully functional calibration department. Bigger ones do, but for the most part, they'll be working with a calibration company to verify a lot of it. And then for ratio or intervals, think about wear and tear. Micrometers and calipers are going to see more wear and tear, using them a lot. Maybe Joe blocks are not, because you're only stacking them and maybe checking calibration with them. So typically extending the calibration period for solid gauges and shortening it for moving gauges. That's just my preference, and that seems to follow some of the industry as well. And of course, there are alternatives. I mentioned you get to design your own system, and you can justify it however you want, as long as you can reasonably justify it. So, in terms of record keeping, again, just to reiterate, you need the gauge ID, manufacturer, style, model, serial number, location, where you're using inspection, production, What standard are you using is very important. You need to be able to trace it back to the standard that you're choosing to calibrate against. What your procedure is should have some sort of serial number associated with it, or a title that you can say, yes, I'm calibrating the micrometer according to procedure XYZ, which is available to everybody who does calibration. You're going to need the date of last calibration, current calibration date, your next calibration, and your interval. So really, the current calibration just means, are you currently within calibration status? Is it passed or failed? You need to be able to answer that question if somebody asks you, what's the calibration of this? What's the status of this gauge? Is it in calibration or not? For the reference standards and traceability numbers, you need the ID numbers of your standards, the calibration dates of those standards, and the standards that you use to calibrate those as well. You'll need to record the measurements you took, the adjustments you might have made, and any damage or repairs that were noted and performed. So I have an example. A former student of mine very graciously sent me one of his calibration records. This was, I believe, for a micrometer. Yep, so it's for a micrometer. Datum Technologies in Santa Clara. Pretty cool company. I've talked to some people from there, and if you're in that area and you need some machine parts made, please look them up. They've I think you'll be impressed with what they do in terms of machine parts. So they've provided one of their calibrations for a micrometer, and if we kind of go through this, the calibration has a number itself. I should point out, all the blue squares, I have redacted a little bit of information that is not necessary for this lecture, but it does pertain to the calibration company itself. Don't necessarily need to involve them in this video, so just removing in case they don't want their information out there. But either way, they have their company address, they have their name and logo, their certification number, so you can trace it back. You have this piece of paper and you say, oh man, I lost my certificate. Can you send me a replacement? It's this number. Just give them the number, they can send you a replacement. The Datum Technologies address is here. The date that the calibration was performed, February 24th, is here. You have a control number. The calibration company assigned their own control number. Datum Technologies assigned a control number, DT155. So Datum is tracking it, DT155, and the calibration company is tracking it with another number, but they're cross-referenced, right? They're cross-referenced on this document so they can be traced to each other. We have the gauge type micrometer, made by Mitutoyo, model number, size is 0 to 1, same size as this one here. The temperature and humidity conditions under calibration, the location performed at their facility. There is a work order number associated and a purchase order associated. Serial number for the gauge, so that would be actually engraved by Mitutoyo somewhere on the gauge, usually the sleeve for a micrometer. Received condition, intolerance. Return condition, intolerance. Intolerance. So, once again, cal date, February 20th. Calibration interval, 12 months. Due date, February 20th, 2021. So this calibration is a different approach than what I've explained to you. I said I like to do these in-house every 3 months. Datum Technologies is sending these out every 12 months. And I could justify both approaches. I know Datum Technologies will be checking their micrometers with a standard before they use them. So they're not waiting 12 months and never checking their micrometer themselves. But they want that extra traceability, that extra security in having a third party verify their micrometer once a year, which is a great way to do it. I'm not gonna complain about that at all. So if you want to do it in-house, you've got to get your calibration block sent out. So sooner or later, you're sending something out. Data and Technologies is sending out their micrometer and checking it in-house before they use it, so that they're not having to wait a year to find out, oh, it went bad. They're finding out right before they use it if something went bad. On the next bottom of the page, continuing this example, they have the standards used to calibrate their equipment. So they have an ID number for the equipment that they used. It's a gauge block set. It was made. It's a model number, serial number. It was made by Starrett, and its due date is July 25th, 2021, which is well into the future of the calibration date. And there's a traceability number right here. So if you need to pull the information on this calibration, you can contact the vendor and ask them, can you get me the information relative to this number? And they will trace it back, and you can keep going if you need to. And some companies need to do this before they award contracts, before they accept product. They'll go through the method of tracing back the gauges. So it's really important to maintain it. And then they have a procedure. So it had an ID number. It has a description for micrometers. This is what the calibration company used to verify. Then the technician signed it, and the supervisor or QC approval signed it. And on the bottom here, with a bunch of mumbo jumbo, legal stuff, this states the ISO. Again, they have 17025 and ANSI NCSL 2540. So these are the standards that the calibration lab are using to calibrate pretty much all of their gauges. And they will have certificates, audits. They will have passed audits on standards to verify that they're doing the right work. So we'll talk about the chain of calibration. Again, I just went over an example now and earlier. Every link must be calibrated. The gauge, the working standard, the next standard up, the next standard up. They all need to be calibrated. And if a higher level, fails, everything below it becomes in question. So it's really important to not fail. And if you are going to fail, this is at the most risk. It's also at the lowest chain, right? Well, this is connected to all your product, obviously, but if the gauge calibration company had something that failed, there's a lot of gauges associated with that failure. So gauge calibration companies are very careful with their equipment and maintaining calibration. And then again, what happens when a higher level fails? Something went wrong between the last calibration and the current, but when did it happen? What about all those gauges? What about all the parts that were associated with those gauges? There's going to be a lot of re-verification, corrective action, root cause. There's going to be a lot of investigation going on by the calibration company, or hopefully it wasn't the calibration company, but I've had gauges fail all the time. It's unfortunate, but it happens. You need to be prepared for it. And if you've got a traceability chain, then you won't have it. You won't have as hard a time as tracing it. So one of the reasons why calibration intervals tracking and traceability is simply to avoid these problems. You're basically saying, we figured out if we measure the calibration of this gauge at this interval, it always maintains calibration. If it always maintains calibration, we don't have to do these investigations, which is great. If you extend calibrations and then they fail, well, then you've got to do investigations. So you shorten them to make sure you don't. Then, that last bullet point, or that fourth bullet point, when deciding if you need to re-verify other gauges or parts, there's always a trade-off between the expense of that and the risk of it causing a problem. So I'll give you an example of, I go to verify this micrometer and it's out of tolerance by 3/10,000ths, which is large for a micrometer. But you think to yourself, all right, is 3/10,000ths of an inch going to affect my final customer? If my parts are reading differently by 3/10,000ths of an inch, is it going to be a quality issue for the final customer? You get together and you discuss and you look at what parts were made with this micrometer, measured with this micrometer. You discuss their tolerances. You discuss any measurement data that you had and see if that would have been some of it goes out of tolerance. And then sometimes you say, okay, yeah, we gotta remeasure these parts with a calibrated gauge. Other times you say, well, the risk is low. If there's a problem, final assembly will catch it before the customer. Or if there's a problem, final assembly can adjust, make a correction that is acceptable for us. Or they'll screen it. Final assembly will just screen out the bad ones. Whatever your approach is going to be, you may not do a re-verification of the parts. On the other hand, you might have precision parts that could affect your customer, and you will need to. So it becomes a trade-off and it becomes a discussion in your MRBs. And best way to avoid it, obviously I've said it, check your gauges at your shop floor level with your working standards before you use them. Have good condition working standards every day. Check your micrometer. Okay, micrometer's good, I'm going to use it today. Maybe in 3 weeks it's like, hey, it's a little bit off. Maybe some of the parts I did are a little bit off. You can verify those. Maybe they're still with you. But if you check it every day, there's only a small window where you could have made bad parts, and it minimizes the chance of doing something, or it minimizes the impact of bad condition gauges. So we're going to kind of wrap things up now. I haven't talked about the calibration environment much, but environments is really important. So I've talked about traceability and methods, but actually the environment, the temperature and the humidity of the room and the gauge will have a big impact on measurement accuracy and calibrations. So generally speaking, you want everything to be the same temperature in the same room. A 24-hour bath in the same environment is a good idea. It's not necessarily required at all times if you can achieve it other ways, but keeping the tools and the calibration standards in the same locations, keeping the master standards protected and away from production, but still in the same environment, means you can check them against each other. And you want to calibrate in the same location that they're going to be used. So you don't want to calibrate in a room that's colder than where they're going to be used, because as soon as it leaves that room and it goes to production and it's warmer in production, the metals expand and it doesn't read the same as it did in the calibration room. But if you are gonna pick a temperature, you don't have to pick a temperature and humidity. But if you are gonna pick something, first of all, pick something you can maintain. It doesn't have to be an exact temperature, like I have on the screen here. But pick something you can maintain. If you are gonna aim for something, the typical numbers that people aim for are 20 degrees Celsius, 68 Fahrenheit, and humidity less than 50%. So if you can't maintain that, maybe you can maintain 72. As long as you can maintain 72 year-round and you do all of your calibrations at 72 and your measurements at 72, that's fine also. But the industry, the ISO standards that calibration labs use will be 20 degrees Celsius, and humidity will be less than 50%. If you're calibrating electronic equipment, calipers, voltmeters, hardness testers, portable hardness testers, whatever, that temperature is going to be 23 degrees Celsius, 73 Fahrenheit, and humidity between 25 and 80 degrees. And that's just what works good for electronics. But again, you can maintain whatever you need to and whatever you're capable of. So One of the reasons, I haven't really talked about humidity, less than 50% or 25 to 80. Humidity has a big impact on light traveling through the air, and how much water is in the air, causes the light to refract and diffuse. And so it decreases the accuracy of any light-based or laser-based measurements. So they need it relatively low, but not so low that the air is dry. If the air is dry, down at like zero humidity, people get uncomfortable. You don't want to be working in that. So that range is not just for the instruments, but it's also for the people involved in the calibrations. So I'll close with some tips. I want you to keep in mind, a gauge that is out of calibration interval does not mean it is bad or that it cannot be used. Traceability will be lost, but oftentimes the gauges are still functional. So what that means is sometimes you have a micrometer and it's out of the calibration interval, which means, let's say it was supposed to be calibrated last month. You go to use it now and the sticker says, ooh, it was supposed to be calibrated last month. It hasn't been updated. What some people will immediately do is say, oh no, it's out of calibration. You can't use it. And that's the wrong attitude to have. What that means is you need to check the calibration. And once you do that, if it passed calibration, well, that still a good gauge. You can still use it. Just update your records, and you'll need to address that gap, with some sort of investigation. But if it was still within calibration when you checked it, then it never actually was physically wrong. The computer system or the tracking system that was used to do the intervals, something went wrong there. It didn't alert you to the problem, but you probably will find this in your careers, that gauges get overlooked, and it doesn't mean you can't use it. It just means you need to calibrate it first and do a small investigation if it passed, and do a larger investigation if it didn't. Number 2 is also very important. A gauge that is within calibration interval does not mean it is good. Gauges go out of spec between intervals. So you could, if we use our datum technology example, they have a calibration for this once a year. So it would be a bad idea to look at the sticker and say, hey, it's within calibration, I'm going to use it. For the entire year, that would be a very bad idea, because sooner or later, gauges do go out of calibration. So check it continuously. Even though the sticker says it's within calibration, just keep checking it, because they do go out of tolerance. So get in that habit of checking it before you use it. Do not just trust the sticker, right? The sticker is just a sticker. You need to physically verify it. And feel free to adjust your intervals as needed. Shorter intervals or longer intervals, depending on how much you're using them and costs and all that. We talked about that. If a gauge is continually failing calibration, instead of fixing it and putting it back into rotation, consider replacing it or repairing it. I've dealt with a lot of gauges that they get a lot of use, they get a lot of wear, they get a lot of use, and you're constantly adjusting zero because everything's looser, everything's worn. And sure, you can adjust it back into zero, but oftentimes it's not worth the expense or the risk. So oftentimes the parts you're making are going to outweigh the cost of replacing the gauge. That's not always true, but a lot of these hand tools you're using on more expensive parts, at least in a run of parts, if not each individual one. So just consider that some are not worth the effort of keeping around. There is a useful life to all these gauges. Now, we haven't talked about for reference only too much, but for reference only means the gauge cannot be used for final acceptance. But it can be used at earlier checks, by production, or on the machine. But as the final quality control person, whether you're the production operator doing final quality or you're a separate person, You can't use reference-only gauges for that final check, but you can use them in, intermediate steps. So, there's a lot of gauges, tape measures, scales. Those can be for reference only, but when you go to do the final check, you need something calibrated and in the system and traceable, okay? If it's for reference only, it's not traceable. And that's just, that's just the way it is. So you want your parts traceable to your gauges and your gauges traceable back to their standards. If you're going to make homemade gauges, maybe you're going to grind an angle or make a thread gauge, you should probably use those for reference only. If you are going to, if you're really going to put some effort into making those homemade gauges, you've got to put them in a calibration interval and have a method on file. And you're going to have to be able to pass calibrations according to accepted steps. So oftentimes homemade gauges are those intermediate gauges during the production process. And then when you're at the end, you have some other method of verifying it that's traceable. Keep in mind your equipment and calibration is usually worth the time and expense. The costs are relatively small in comparison to most gauges and the parts being made, and that's true. As much time as you're spending to calibrate and the money you're investing, for outside labs to help you verify, it's almost always worth it. Especially if you've gone through the effort of choosing your intervals correctly, it's going to pay off because every failure you have product recalls, you have investigations, you have corrective actions, and it's so much easier when stuff stays in tolerance and passes each time you check it. So just keep that in mind. Sometimes it's a high expense, but consider that when you're investing in your metrology equipment, that there's an associated calibration on an annual basis that you just need to be aware of and prepared for. And sometimes, the cost of calibrating this gauge over its lifetime may be more than the gauge itself, but it's worth it. Calipers, these have gotten so, calibrating gauges the cost of these gauges has dropped. Calibration costs are still relatively the same. They don't get easier to calibrate because they're easier to manufacture. So over the lifetime of a caliper, you might spend more money calibrating it than when you originally purchased it, and that's just part of it. So I want to thank you guys for watching. I hope you enjoyed this video, and please check out my other videos on the Pragmatic Metrology website. Got more concepts to help you choose gauges and read blueprints and how to make the right decisions, as well as a bunch of gauges, calipers, micrometers, surface plate, many more. So please check out that website and check out my other videos, and thank you for watching.